All right, let's talk a little bit about analyzing the latent image, which is chapter 25 in our textbook. Here's some learning objectives I've got for us today. We've got a bunch of different variables. So this is kind of a recap lecture. We're going to be looking at all these different things that we've talked about over the last 2 trimesters. So anything that the technical parameters that we have control over, and also some of the ones that we don't have control over that affect things like image exposure, contrast, noise, sharpness of detail, magnification, distortion at the image receptor. Okay. Then we'll define resolution to include both spatial and contrast resolution. We've done enough learning now to really get down to the nitty-gritty with that, talk about how it's measured, and then we'll talk about some limiting factors that are impactful for digital systems. So exposure. Looking in our textbook, as we're thinking about the latent image, I'm looking on page 377. What we're interested in, anytime we're working with an imaging system, is the overall ability of that imaging system, whether it's digital or what have you, the overall ability of that system to bring out the maximum number of details in an image. And we'll call that resolution. That's the bottom of the first paragraph. Okay? So almost everything that we're dealing with today has some kind of impact on resolving what we're trying to see, making diagnoses. And when we're talking about the latent image, we're talking about any information that's captured prior to whatever developmental process we use, whether that's a digital developmental process or computed process or film screen process. The latent image is what's there that's held in the system. And so in some ways to think about it is it's like the purest capture point of what exited the patient. So one way to think about it might be it's like the remnant beam. It's what we captured as the remnant beam. Anything that has not yet been processed, we will call the latent image. It's latent, it's there in the system, it has not yet appeared to us. So that's what we're talking about today. And as we're thinking about exposure, we're going to use actual images to consider exposure. And this is what this chapter is doing on these first few pages, like page 378 to 379, is a whole lot of work, right? Like there's a whole lot of dense material on these 2 pages. It's pretty much 2 trimesters worth of information condensed down to 2 pages. So I've reread these 2 pages probably 10 or more times, just because it encapsulates a lot. And I've broken it down slide by slide for us to try to make sure that we're as clear as possible on each one of these technical considerations, right? So we're going to breeze through this stuff pretty quickly. If there's a point where you're not clear on something, please let me know either by raising your hand or filling out one of these muddy points. But everything that affects IR exposure includes mass, and it is directly proportional, right? So as I increase my mass, then I would expect, if I double my mass, I would expect double the exposure at the image receptor, right? So if I were to pick between the 2 of these images, which has the higher mass, I would probably say it's the one on the right, right? It has more darkening, decreased brightness, in other words, increased exposure at the image receptor. KVP we've dealt with has an exponential effect on the image that results, right? So as KVP increases by 15%, we have double the exposure that occurs. And the reason for that is because it's, again, an exponential increase. I don't have to double the KVP to get double the exposure. I only have to increase the KVP by 15% to double the exposure, right? Because I'm increasing the penetrability and also the amount of X-rays produced when I increase the KVP. So if I were to say which of these has the higher KVP, it would be the one on the right. Okay? Generators and rectifiers both have an effect on the amount of exposure. And so we've looked at that, like, for example, with half-wave rectification. If that's what the generator is capable of, it is going to significantly reduce exposure at the image receptor. Okay? It's actually producing a wider spectrum of energies also than a high frequency. So, yes?
Question. You said something about higher KVP. You said the one on the right?
Yes. Yes. And because I'm not talking about contrast on this image, I'm only talking about exposure. I'm only talking about exposure. So underline that in your thinking. I'm only right now talking about exposure. So don't be evaluating these images for contrast right now. That's a good question though. So it bears the point, right, that as the KVP increased, I see on the image, right, I've burned out a portion of the lung, which might, to an expert eye, say, oh, it looks like a really high contrast image. No, it's just burned out. But generators and rectifiers definitely have bearing on the kinds of penetration, the kinds of X-ray exposure that can occur. So as we increase to a higher frequency generator, like if we move from the department X-ray machines, which are using high frequency, to a portable, which is using direct current, chances are we need to decrease our technique just slightly. That was really apparent back in the day of film, where we had to be very careful if we were using the portable to reduce our technique somewhat compared to what we did in the department. Why? Because of the generator in the portable. It was using a direct current. Protective filtration has no effect whatsoever at exposure within the latent beam. It's really, really important to know that. That's like a board. There's like 5 board questions I could write just about that one point, right? Making sure that we understand how protective filtration works. Protective filtration only reduces the amount of exposure to the patient's skin surface. It only is reducing exposure to the patient's skin. It's only reducing patient dose, in other words. So protective filtration has no bearing whatsoever on the latent image. It is not filtering out any portion of what could be an image-forming X-ray. So just remember, protective filtration, no effect whatsoever. Right? Field size. I know that as I increase my field size, I would expect exposure to increase as well. Some of that's going to be helpful exposure, and some of that's going to be scatter, right? But it all would affect an overall darkening of the image, or an overall decrease in brightness, and either one of those synonymous with exposure. Patient condition. And we'll talk more about this in comparative pathology, but there are certain additive pathologies that the patient might have, and so as we're getting a history, that's one of the things I'm thinking about in the back of my mind. In addition to pathology, I'm also sizing the patient up. I'm thinking, how tall are they? How much muscle mass do they have? How much fat is there in this patient? Does it seem like their bones are kind of thick? Are they a child, right? All of those things have bearing on the kinds of technique that I would employ, because as different patient conditions increase, one of the reasons I've required us to use calipers in the lab and asked y'all to get measuring tapes and things like that is because if you really master a measuring tape, I know that no tech uses them, but if you really master a measuring tape, you will have mastered how to set a technique on any patient with any machine. And that's really true. Grid usage. So as I increase my grid ratio, I would expect the exposure to decrease significantly, right? And we've run into that doing the digital technique chart lab as well. Like, well, did we do this tabletop or did we do this in the grid? Because if we did it in the grid and our last exposure was at the tabletop, we're going to need to probably double or maybe even quadruple our mass to compensate for the grid that we're using. Now, do not make the mistake of using a grid and then increasing KVP, because you pretty much are just fighting yourself at this point. The whole reason we employ a grid is actually to clean up scatter that's apparent in the latent image. And so the other thing that produces more scatter is increasing my KVP. So anytime I'm using my grid, I'm going to be significantly increasing patient dose, because I'm not going to increase KVP, I'm only going to increase mass to compensate for grid usage. So as I employ higher grid ratios, I will be decreasing exposure. So to compensate for that now, I'll have to then increase mass, right? And that's the name of the game with a lot of what we're doing. As we're learning these things, is not only thinking, okay, grid usage does cause a decrease in exposure, is also just thinking about what are the compensations I'm going to have to make with my technique to make sure that I still get a diagnostic image. The anode heel effect has an uneven effect on exposure, and so some people might call it a gradient effect. But in general, on the cathode side of the tube, we will have a higher amount higher percentage of x-rays coming off of that end of the tube than versus the anode, because some of the x-rays are being attenuated by the anode itself, right? And so it causes a lack of uniformity in the x-ray field along the axis of the x-ray tube. So it does have an effect on exposure. It's kind of a weird effect. And we can use it to our advantage. One modality that does that to great success is mammo. If you're ever using, if you're interested in learning about mammo, and that's something that you want to pursue, then definitely beef up on your understanding of anode heel effect. Because if you track with me, if we're trying to image this patient's breast tissue, what side do I want the anode to be on? Think with me. Because I'm going to use the anode heel effect basically as a wedge. So I've said that there's more x-rays coming off the cathode end. Where do I want the anode situated in terms of the patient's anatomy? Further away from the patient. Basically, if I were to thinking about the area of the breast, I would want the anode over the area of the nipple, right? And I would want the cathode end to be closer to the chest wall, right? Because there's more tissue. It's basically a wedge-shaped piece of anatomy. And so since there's more tissue closer to the chest wall than towards the nipple, I will position the anode area over the area of the nipple. We're using then the anode heel effect to create basically a wedge, right, in order to compensate for changes in the patient's anatomy. Of course, the other thing that we do all the time to compensate for the changes in the patient's anatomy, which the patients just love, is compression, right? Because that's another way to solve that problem. Just it's helpful to do those this versus that comparisons sometimes. SID has a indirect effect on exposure, and it's not only indirect, it's also exponential. So as the SID increases, the exposure drops off exponentially, right? So as SID increases, exposure drops off exponentially, and that's covered in the inverse square law. And pretty much any question that we ask technique-wise, we'll have to employ the inverse square law to make sense of it. And then finally, the OID has a funny effect on exposure. We can use the OID. OID pretty much has bearing on almost everything that we do. And it's kind of one of the Jesus answers, like if we're in Sunday school, is like, what's the OID? Because if we increase the OID, we can wind up using the OID as a grid of sorts. We sometimes call that an air gap technique. And so by increasing OID, we can reduce exposure. We can reduce the amount of scatter radiation that's reaching the image receptor and thereby decrease exposure. So as OID increases, exposure decreases. It's not a super noticeable effect, but it does exist. Subject contrast. So we're switching gears, and you can see I'm just moving right through the textbook and just thinking about each one of these things that they've listed out here. Another thing that I feel like this textbook chapter is written directly toward is there's a section of the content specs that just has a table for under image production, and I think I even had y'all fill in the table at one point as part of an activity. This chapter is pretty much the table, right? So contrast is one of those more difficult things. Looking at these two images, which of these image has the higher contrast? The one on the left has the higher contrast. So it looks like they both reach, and it's nice to have the step wedge right next to it so we can kind of see what the different contrast levels are represented using the step wedge. It looks like they have the same range of exposures to the film that's apparent on there. It goes from white to completely black on both images, but there's a differing number of shades of gray. The one on the right has more shades of gray, so we're going to call that low contrast, right? Because from step to step to step is a lower step, right? One of the ways, if that's confusing to think about it that way, we could also say that we could talk about it in terms of grayscale, right? So there's a number of different ways we can think about contrast. But I want to point out that the one on the left is definitely the high contrast image. There's less grays between the white and the black on the image. So KVP controls penetration, which is critical to contrast. So it's not quite accurate to say that KVP controls contrast. That's kind of the assumption that we're making, but there's a number of steps there that we need to arrive at. If we don't understand those steps, we've kind of like failed the physics section, right? So the way that KVP works to control contrast is as I turn up my KVP, I'm increasing the amount of penetrability within the X-ray beam. The average penetrability of the X-ray beam is being increased. If I turn the KVP up too high, I'm no longer taking diagnostic pictures because all of the X-rays would just go straight through the patient and there would not be anything that would show up. There would be no contrast or no imaging apparent, right? If all the photons just went straight through the patient, all I would get would just be a uniform black field, right? If I turn down the KVP too low, then I would have a uniform white field because none of the X-ray photons would be able to penetrate the patient, right? So what we're looking for is an optimal amount of KVP, and by relationship, we're also looking for an optimal amount of contrast. So that's the relationship there that exists, and it's a balancing act that we're trying to coordinate with every image that we take. By extension, the generator has bearing on the penetrability of the X-ray beam. So what we've learned in Foundations and also in Image Eval 1 is that the kind of generator that we're using can produce a different amount of spectrums of penetrability. So again, if I'm going back to the half-wave generator and I'm using a rectification that's only able to rectify like 1/2 of the waveform, right? So I get that rise and that fall for 1/2 of the waveform, and then a gap, and then a rise and a fall. Each time that I have a rise and a fall, that rise and fall represents a spectrum of energies of X-rays that could be produced, almost like a rainbow. It's a spectrum of energies. And since there is that spectrum, right, the lower parts of that spectrum are not going to be able to penetrate the patient, right? So by having a less efficient generator, I will be decreasing penetrability, right? And so by extension, I would be, strangely enough, also decreasing the amount of contrast, right? I would be producing a more low contrast image. Protective filtration, again, has no effect whatsoever on this because what we're controlling as we control KVP is the kilovolt peak. We're controlling the peak energy, and so we're only moving the average energy over to the right. And so anything that, if we're controlling basically what the peak energy is, the highest amount of X-ray penetrability that's there in the beam, any of those high energy photons will pass directly through any kind of protective filtration. And that's why the filtration doesn't have any effect on subject contrast. Field size, again, we've mentioned that if we increase our field size, we are increasing the area for scatter, right? Scatter is the enemy of contrast. So contrast is going to be lost due to scatter, right? So if I had what was originally a high contrast image, if there's too much scatter on the image, it will wind up starting to create so much noise that I'm going to start to lose contrast due to noise. The same thing is what's happening with part thickness, which goes right back to our discussion, our this versus that discussion with mammo. It is the reason why we do compression in mammo. It's the reason why we do compression in fluoro, right? If we can reduce part thickness, we'll be improving contrast. So you reduce part thickness, you will improve contrast. Unfortunately, we can't do compression on a chest X-ray, right? That'd be crazy. So we just have to come up with other ways to make sure that we're getting sufficient amounts of contrast. Patient condition definitely has an effect on contrast. So again, emphasize the need for appropriate history as we're thinking about what that might do on our image. Because if we look at an image and we say, oh my goodness, that image on the right, it looks like the contrast is messed up, when really what the patient has is a condition that's causing that fogginess on the image. We need to be aware of that. Scatter radiation, like I said, is the enemy of contrast, and grid usage exists to clean up scatter. So anytime we employ a higher ratio grid, we will get better contrast. The grid exists to improve contrast. Well, how does it do that? By getting rid of scatter, right? So I said that with the grid usage, it reduces the amount of exposure, but the reason that we use a grid is to improve contrast, right? So there's a tension there. It's a tool that we use. And anytime we're using a grid, we're also increasing patient dose because we're having to compensate for it. Image noise, and this goes back to the scatter problem, right? But anytime we have an insufficient mass, this will make quantum model apparent. It's there in every image that we take. Quantum model exists in every image that we take. But As the ratio of signal to noise decreases, so the amount of signal to the amount of noise decreases, then we are seeing more noise on the image. So the image on the far left has the most noise on it, right? So what did the tech do? They increased the mass, and now we've got enough signal that the image detective system can get rid of the noise that was apparent, right? It's sampled enough stuff statistically to get rid of the noise. Insufficient KVP makes quantum model apparent. So KVP does have some bearing on quantum model. We've said that primarily if we want to get rid of quantum model, we need to increase mass. But KVP also has some hand there in it. Excessive KVP, though, produces more scatter. And if there's one big takeaway from this lesson, it's probably that. Excessive KVP increases scatter. Because I've talked to enough technologists who are out in the field after being in school for a few years, and they've forgotten that point for whatever reason, that there is such a thing as too much KVP. Increasing the field size, again, produces more scatter and therefore produces more noise. So this is the part of our learning that seems like all the text that Campbell's forgot, right? And hopefully this doesn't wind up on KVP, but I mean on YouTube or whatever. But as we increase our field size, we are decreasing contrast. How? Because we're producing more noise. We're relying on the grid to clean up more. Part thickness, right? Anytime as we increase part thickness, this is one of the reasons why we have rules like the 13 centimeter rule, where if the part is thicker than 13 centimeters, we want to employ a grid. Why? To get rid of the noise. Patient condition. Again, this one's probably here on every single one of them, because a lot of what we're doing is trying to work with patients in order to make sure that we're getting an appropriate amount of diagnostic information. Grids reduce scatter, but they can also produce an artifact. We looked at that some last week, that as we employ grids, we have to be careful and make sure that, for example, that the wall bucky is selected, that we have sufficient mass to compensate for the grid usage, and that we haven't angled the part in relationship to the grid or the grid in relationship to the central ray, because that can produce artifacts due to the grid not being at the correct angulation. Interestingly enough, as we increase the OID, we are decreasing scatter. So we can use what we call an air gap technique. We do that most commonly on stuff like a lateral C-spine. And then motion generates an artifact. Motion is probably the easiest way to ruin an X-ray exam, right? So we kind of take it for granted that all of our patients are going to be as still as possible. And if you look at the very first X-ray exams that were done, apart from Rankin's wife hand, that was all of like mummies. Why? Because mummies are really good at holding still, and they had exposures that were like 12 minutes long, right? But definitely, as you're talking to your patient and you're gathering or gaining a rapport with them, remind them how important it is to hold still in a way that they'll understand. Sharpness of detail. So I like these two images because they really draw out what we're talking about when we're talking about sharpness. The image on the right really pops, right? The edges are very, very clear. It has a sharper image. Now, interestingly enough, this sharper image was produced by a computer program. It's nothing that the technologist did. They used a post-processing program to sharpen the image. So we'll learn more about how that works later on. But for right now, image 1 is image 2 in this case. The tech didn't do anything. They took image 1 and they ran it through a software that produced image 2, right? But there are a lot of different variables that affect sharpness as well. So there are ways that we can improve sharpness without any kind of post-processing. Focal spot size is the primary control for sharpness. Now, I'll say that again. Focal spot size is the primary control for sharpness, all right? That's pretty much all focal spot size does. There is a point of confusion here for a lot of students, though, because they recognize or they remember me in the lab saying, don't use too high of a mass on the small focal spot size, right? And so there's a mistaken assumption there that somehow focal spot size has something to do with exposure. It does not, right? Let me emphasize that. Focal spot size has nothing to do with penetration or exposure, period. It has nothing to do with penetration or exposure. It only controls sharpness, period. That's all focal spot size does. They're going to try to trip you up with that one, right? The only reason that I've said is be careful, don't set too high of a mass with the small focal spot size, is because we could inadvertently burn out that little tiny filament. And we don't need to be burning out filaments. That means we have to buy new X-ray tubes. So focal spot size has no bearing on the amount of exposure or penetration. But there's a technical limitation. Anytime I'm employing a smaller focal spot size, within the engineering of that tube, I need to be careful that I don't overload a heat unit, right, and blow out my tube. That'd be a problem. So, anode bevel, interestingly enough, affects the projected focal spot size. So this is the amount of angulation in the bevel, or angulation of the anode itself. But as we increase that anode bevel, we kind of run up against a limit ourselves, because as we're increasing the bevel of the anode, we're increasing anode heel effect. So there's some pretty standard anode angles. This is really one of those ones for the academics and the people at the colleges to sit around and think about. I wouldn't burn a lot of brain cells on this one. Just know that anode bevel does affect the projected focal spot size, just through geometry. The SOD to OID ratio controls sharpness, and we've done some of those problems already in this class. We can do formulas where we actually figure out what is the sharpness based on this ratio, and it has largely is controlled by the geometry of penumbra versus umbra, right? Motion causes blur, and exposure time can affect it by giving room for motion, right? So one of the questions that I like to ask and the registry likes to ask is, which of the following techniques would be best used on a pediatric chest x-ray? The assumption there is that the patient's more apt to move, so therefore I need to be using a shorter exposure time, larger MA, shorter exposure time, right? Why? Because I'm reducing the amount of potential for blur and improving sharpness. Okay. We're winding this up with, I think, just two more things, and they both have to do with distortion. The first is size distortion, which we call magnification. Magnification is completely controlled by the ratio of SID to SOD, right? So remember that however you need to remember it. But there's some things that we can control the SOD of, and there's some things that we can't, right? We can always control the SID, but for example, with the chest x-ray, if I have to shoot an AP, I can't necessarily control the distance from the source to the object being the heart, right? So the way that we control for that in ideal situations is to do it PA, right? To just flip the patient around. So there are positioning considerations with everything that we do. Like there's been a lot of debate during procedures about which is the best way to do, for example, Y-view shoulder. Well, my answer is which one has the shortest OID? Right? Because that has the longer SOD, so there's going to be decreased magnification, right? The magnification is not always the enemy. It exists on every image that we take. But the question is, what is magnified and why is it magnified? Is it magnified because we need it to be magnified, or is it magnified because we just didn't understand what we were doing? So positioning influences this SID to SOD ratio. Use it to your benefit. All right, now this one is kind of the truly evil form of distortion, which is shape distortion. It is never really a useful thing to have accomplished, right? Because we're actually distorting the distances between things, and we're making the bone appear to be longer or shorter than it actually is. And I think I even used this image on a test to ask you about identifying different kinds of distortion. So if we assume that the image A is a image without any distortion on it, then image B is clearly what we would call foreshortened, and image C is elongated. And it's interesting to look at the elongated image in particular because it's clear that the distortion has also caused the humeral head to shrink, right, while the more distal part has increased in size. So knowing that, we can even imagine what the angle of the X-ray tube was in relationship to the part. It was basically angled cephalically, which has caused the humeral head to appear to be smaller. So alignment of the beam, the part, and the image receptor is the controlling factor for shape distortion. And a lot of times the way that we think about it is similar triangles, that we're making triangles And we want, if nothing else, to be as perpendicular as possible to the area of interest. So there are times when we can avoid distortion, but we want to maintain some degree of perpendicularness, which is still an angle, right, to the area of interest. Position is a primary way that we affect this, as well as the angulation of the tube. All right, I'm going to switch gears now. And that was kind of a recap of almost everything that we've discussed in the last 2 trimesters, right? Kind of the final piece of the puzzle here for this chapter is a more in-depth consideration of resolution, which we've talked about a little bit, but we'll now define more carefully here. So I'm just going to call it the ability to distinguish between individual parts of an object. That's all resolution is. It's just the ability to distinguish between individual parts of an object. If we want to get more into the nitty-gritty, we can talk about the distinction between spatial resolution and contrast resolution. I think about spatial resolution as having to do with space or with size, right? So is the ability to distinguish tiny objects, right? Why? Because tiny objects are very, very small in size, and in general the distances between them are also small. So that's why we call it spatial resolution. This is measured by spatial frequency. It is expressed as line pairs per millimeter, so we can actually tell you what the line pair per millimeter spatial resolution is of any system that you're working on. Even if you or none of your techs in your department know what the spatial resolution is, the physicist does. It's something they have to record every year. And for an example of it, if you turn to page 383 in your textbook, you can actually see the kinds of resolution test strips that we use. And there's one that is, and what I like about this is we see side by side 2 different test strips, one done on a large focal spot size and the other one done on a small focal spot size. And we see with that focal spot size difference on the same system how the small focal spot size has better spatial resolution, right? As we're going down the lines and we're looking at where exactly do the lines become so blurry and indistinct that we can no longer tell where a black line starts and a white line begins. If I look at the large focal spot size, I don't scan down very far before the image starts to get blurry to my eyes. Versus over here on the small focal spot size, I can scan down further before the image gets truly blurry. Now, if you wear glasses or you're struggling to see a distinction between these, that's okay. Because what we will do is we'll use ROIs, or we'll figure out a way to measure it, and we can know based on the measurement of the ROI whether or not the system is performing appropriately. Okay? So just know we used to use a slightly different system to do that. If you need an example of what this actual test mechanism looks like, it's right here on the bottom of this page. And that is, if you remember back from some of the labs that we were doing in the spring when I said we need like a redneck spatial resolution template or something, I used some little tiny fine wires on the thing. This is what I was trying to approximate. So I have since asked for budgeting to purchase 2 of these things so that students can see more clearly what we're talking about as we're measuring spatial resolution. And we can actually come up with an actual measurement. This is the number of line pairs that I can see. All right. Contrast resolution, we're going to define as something completely different. Even though they both have resolution on them, they are completely different things that we're talking about. Contrast resolution is the ability to distinguish objects with similar density. So I'm not looking at things that are very, very small. I'm looking at things that are very, very similar in their amount of density. Very, very similar in their amount of density. So this is measured largely by the modulation transfer function. We'll talk a little bit about that. It's expressed as a number less than 1 but greater than 0. And if we want an example of what it is I'm talking about, if we look on page 384, figure 25.8 shows us some of what we're dealing with, and I would encourage you to read through this. It's saying that as we're looking at the line pair template, we're not just interested in how small the lines are that we can see, we're looking at how much gray is now starting to show up between the line pairs. How much gray are we seeing? Because that is that penumbra effect that exists from line to line. If you need an example of what the actual readout is or how we compare modulation transfer functions, it's on the next page, 385, but we'll talk about that more in just a sec. So spatial resolution, again, I've said it is the smallest absolute object size that can be reproduced and it is inversely proportional 1/2 the spatial frequency. It's fine. Do you need me to get it for you? Okay. So we're dealing with little tiny objects, and we can actually do a formula. We can say the minimum object size that this system's able to reproduce is 1/2 times 1 over the spatial frequency in line pairs per millimeter. So we can just plug and play on that formula, and there's actually a place to do that on page 382. Practice exercise. I would encourage you just to familiarize yourself with that math. It will be helpful to know that math. So if I'm given a system and I want to know whether or not the system's going to be able to look at something very, very small, I can plug it into this formula. Measures of spatial frequency are done using a line pair resolution test pattern. And I've indicated that there's one possible line pair resolution test pattern, which is on page 382. Here's an example of another, so I'll zoom in on this. You can see we've done this on a foot phantom, and we've compared it to this other kind of line pair test pattern. And this one's red. Rather than looking down the page, I'm still looking closer and closer towards the center of the cone, right? And we have a moire artifact here. You can see this kind of blurring of the cone lines where it looks like there's actually an additional pattern. That additional pattern is not there. It was apparent to the digital imaging system, but it's not there in actuality. But we're looking for at what point does the image become so blurry that I can no longer see one line from the other, right? And that lets me know exactly what my spatial resolution is for my foot x-ray. So we'll call that a spatial resolution or line pair resolution test pattern. And like we said earlier, focal spot size is the primary limiting factor for spatial resolution. I'll say that again because it's worth repeating. There's actually a historical note here it's worth kind of comparing between two systems. So with film has much higher spatial resolution than a digital system. Because if you think about it, a film is just made out of little tiny crystals, and all those crystals can be brought very, very close together, almost like stuff inside of Jell-O, to where one crystal's right on top of the other crystal. And all these crystals are built to absorb X-rays. That's what the crystals are there for. So a film is full of little tiny crystals that are built to absorb X-rays. There is no way I could wire up a digital system where the receptors of the digital system are smaller than those little tiny crystals, right? Each one of those little crystals can receive an X-ray. So the digital system is always going to have pixels that are larger than film. So what that means is film will always have better spatial resolution than digital. Is that a problem? The answer is no, it is not a problem. Why is it not a problem? Because of what I just told you. Focal spot size is the primary limiting factor for spatial resolution. Because the focal spot size is always a real point, and that real point is bigger than the detectors that I use for digital, it is the primary way that I'm limiting my spatial resolution. If I could somehow produce a true point source of radiation, right, that is just a single tiny, vanishingly small source of radiation, and I'm using that for producing X-rays, then yes, I would want to go back to film, right? Because now I'm using such a tiny, tiny source of radiation, the spatial resolution's an issue again, right? But because it doesn't matter what X-ray tube I'm working on, the limitations in the engineering of the X-ray tube is such that the focal spot size is the primary limiting factor. It's the largest thing in the system, is the focal spot size. Doesn't matter if I'm using digital or film, right? What matters is, am I using a large or small focal spot size? Okay? So knowing that tells us why we eventually opted for digital and why the push is towards digital. Because digital has what compared to film? It has much higher contrast resolution. Its contrast resolution is off the chart, which is what we've kind of, almost every lab that you've done in my class has reinforced just this point. So if we want to think back on how do we know this is the case, we can think about, for example, the lab where I have you do an exposure at 500 mass or something like that, 200 mass versus 20 mass, right? We bumped the exposure up to 10 times what it needed to be. Did we still get an X-ray? Yep, we sure did. we would have burned the X-ray film out 10 times over, right? But we still got an X-ray. Why did we get an X-ray? Because the digital system is that good at contrast resolution. It can, as long as you're sending a signal, it is resolving that into a whole lot of grayscale, right? Depending on what the pixel depth is. So that loss of image contrast that we see when we're looking at, I've just blown up the image from the last one, but as we're getting closer and closer on these lines, and I'm going to zoom in one more time, there's a point here in these lines, right, where I know it's kind of blurry, but there's a point where I can no longer see white. All I see is gray, right? So up here I can see some white, but as I go further down, I'm starting to see just gray between the black lines. That point is the point where we've lost contrast resolution, right? And that loss of contrast resolution at this microscopic scale, I've had to zoom in really closely to look at it. And y'all have seen that technique in your labs as well, where I've zoomed in and said, okay, what can we still see when we zoom in? This is due to the effects of penumbra, right? It's due to the effects of penumbra. So images, as we're producing these images of objects within the patient's body, the objects are producing some penumbra. There's a shadow, actually, of the shadow that we're producing. So we use the modulation transfer function of the system to give us a measurement of contrast, right? It always falls between 1 and 0. 1 would be perfect, that the contrast of the object is exactly tied to the contrast that's apparent on the image. That would be a 1-to-1 comparison, right? No system is going to ever have that, right? It'll be some range between 1 and 0, right? So we would hope it's a little bit higher than 0, but it'll never get as good as 1. If you need an example of what those curves look like, you can look on page 385 in our textbook. And we see that curve B is superior, right? And I can say, well, how do I know that that's the case? I'm looking at on the y-axis of this chart, I've got the modulation transfer function. I've said it ranges from 1 to 0. On the other side, the x-axis of the chart, I've got the spatial frequency, right? So what are the line pairs per millimeter apparent on the image, right? And what we're seeing is that B, at the end of the day, has 8 line pairs per millimeter that's apparent on an image done on that system. That means it has a higher spatial frequency. It also means it has a higher contrast resolution. But I don't want us to get confused on that point. The modulation transfer function is largely employed for letting us know what is the contrast resolution of the system. Okay? And the reason we're using spatial frequency to consider it is because we're looking at the gray scales that are there, the apparent gray that's between those line pairs. Okay. So digital systems, at the end of the day, I've said they have a lower spatial resolution than film, but they have much, much, much higher contrast resolution. And almost every lab we've done in this class has reinforced that. Thank you so much. I did want to share this image with you because this is something that still happens sometime in the OR when we print off films and things like that. This guy is using the X-ray that he's rolled up into a tube to view this other X-ray, right? And what he's basically doing is he's hot spotting the image. We used to actually, when we burned out film X-rays, the doctor would say, let me look at it under the hot spot. And they had an actual hot lamp that they would put the X-ray under and see if they could still see what they needed to see. This guy is using a similar technique with just a rolled up X-ray film to see if he can see what he needs to see, a little tiny detail in this image. Thank y'all so much.